example number 4, or reaction number 4, we're going to take alkene plus dilute acid in alcohol. All right, the last example we said H2SO4 in excess water. We'll use H2SO4 again. Let's use the same alkene we used as in our last example that we just revisited in our question here. Let's take sulfuric acid. And let's use methanol as our solvent. If the problem's written like this, it means that we're reacting our alkene with another reagent, H2SO4, and we're doing it in methanol. And this tells us that there is excess, and that means that this is dilute. How about this for the exam? I'll just write the word dilute sulfuric acid on a problem that's dilute, such as one in water. The only difference was the second one we did, where we're using concentrated sulfuric acid. So if we just see these two things, there's obviously no water, no methanol, no anything else to add. You just have to react these two. But if we see a problem like this, plus I'll write dilute sulfuric acid, and I'll probably just write solvent like this, it means that you have to know there's lots of this, not much of this. Okay? So that's how it'll work. And we're going to change one minor thing here. We're using same dilute acid, using the same alkene we just used. And instead of water here, we just added methanol. Let's do this mechanistically. There's an acid-base reaction between the pi bond and our strong acid. We know that it's going to primarily choose to go to this position 1 that I'm calling it, because it'll make a carbocation at position 2 in this case. 1 and 2 is just arbitrary. We call them A or B, red or green, blue or purple, 1 or 2. Roman numerals or not, doesn't matter. This is just to differentiate. So if we make a carbon-hydrogen bond here, we make a carbocation there. Let's do that. This is the compound we make. If we made a new carbon-hydrogen bond here, let's just say that this was carbon number 1. And now I'm just going to condensed format because there's no need to draw this stuff out anymore. It's the same structure as if I drew out the 3 hydrogens here. This is our tertiary carbocation. The other possibility would be to make a primary carbocation here, and we simply know that's not a viable option. Now, at this particular stage, we have a huge excess of methanol. Lots of this. Of course, we have sulfate, but we don't have a lot of it, just a tiny amount. And so, just like with water, methanol can donate its electrons here. And we're just going to draw the result. This wants electrons, this has electrons. We're just going to make one bond. We're going to make that one bond. And we're going to logically see where we can go from there. So this one bond that we've made is this one. Comes from a pair of electrons on methanol. Everything about methanol, else about methanol, stay the same. We see that we have an oxonium ion again. This is very, very acidic, this hydrogen. We can pull it off either with methanol, which there's a lot of, or the conjugate base of sulfuric acid. You can use either one, but I really like using the conjugate base of sulfuric acid. May not technically be perfectly right, but no one can actually witness what this reaction is, so no one can really tell me that it's wrong. So, this is highly acidic, this proton. As we pull it off, these electrons will go back to oxygen, just like we in any sort of other acid-base reaction. We would regenerate H2SO4. So we remake this, but the key product we're making here, instead of making alcohols, is now we've made ethers. So by switching the solvent from water to methanol, we've made a methyl ether. So this is really a very, very close variation on the last reaction we did in water. The last reaction we did was in water. Water added, we had this oxonium on. When an acidic proton gets pulled off, we're left with an alcohol. In this particular example, though, when we add an alcohol, one of the groups is already an alkyl group, in this case methyl. Still one acidic proton. The acidic proton is what gets plucked off, and we make an ether. So examples 3 and 4 are very closely related to one another. In example 3 is a variation if we just used sulfuric acid, which was 2. And sulfuric acid was a variation on the first thing we used, which was HCl, HBr, HI. These 4 reactions go together in perfect logical succession. So if you study them in order, they're a little bit increasingly more complex with each reaction, but they have many more similarities than they do differences. Our 5th reaction changes gears. We'll spend some time with this, the remaining time we have together today. And this will prepare us for what we're going to do tomorrow. So first 4 reactions, very, very important, all with strong acids playing a role, breaking the pi bond. The 5th reaction we're going to do is we're going to do an alkene plus Br2 at low temperature. Okay? This is going to lead to adding 2 bromine atoms across double bond. So this is a very, very generic scheme. These are our 2 reagents, an alkene, bromine, very, very low temperature. This tells us there's no radicals involved. To make radicals out of bromine, you'll recall that we had to apply a lot of heat, 250 degrees or high energy UV light. That would break bromine in half into single electrons. We did all those reactions with alkanes. Now we're doing all the reactions with alkenes. We're not going to do radicals. Something different is going to happen. And Br2 is going to behave a little bit like HBr or HCl or HI, but Br2 is definitely a little bit different. It's not a strong acid. So let's start this reaction with cyclohexene. And we'll draw out Br2. Just like this. And it doesn't look like at first glance that this should do anything. When we had HBr, let's just put this in parentheses, we know that this molecule is polarized this direction, so we could tell where these electrons would go to. But this particular molecule, dipole moment mu is equal to 0. It's not polar, but bromine is very electronegative. Very electronegative. And there's another word about these 2 particular atoms. It's polarizable, but that word's not so important. But the point is, bromine wants electrons always. Bromine wants electrons always. And this particular bond, if we look it up, we know it's very, very weak. We can actually look this up in chapter 12 when we were talking about radicals. We can find that the bromine-bromine bond is very, very weak. And bromine wants electrons. And this pi bond has electrons. And when you expose alkenes to bromine, something weird happens. They start to react. Same first arrow as if we were pushing to HBr. If we were pushing to HBr, this bond would break. Same thing happens here. For slightly different reasons. This isn't a polar bond anymore, but this is still electronegative. If we form a bond to bromine, bromine doesn't want 2 bonds normally, it wants 1. This bond breaks. And previously, we would start building up a carbocation. Notice how this particular double bond is the same at both sides, it's symmetric. There's really no position 1 or position 2, they're both the same. If we were to make a carbon-bromine bond at the top, we'd have a secondary carbocation. If we're making a carbon-bromine bond at the bottom, we'd have a secondary carbocation. So we know in this particular molecule that we're going to form a new carbon-bromine bond. We're going to break bromine-bromine bond. And the other thing that's unique here The other thing that's unique here is that technically we're building up plus charge, let's say on this carbon. And bromine actually has lots of electrons around it. Unlike hydrogen, bromine has lots of electrons around it. Something really special with bromine happens. We're going to add one more arrow to the mix. First, pi bond breaks like normal, goes to an electronegative atom. That electronegative atom is bonded to another electronegative atom. That bond breaks. We're going to be building up plus charge on this molecule. And what happens is, bromine uses one of its pairs of electrons to bond back a second time to carbon. This is quite strange. But let's think about what it means. These three arrows tell us what we should draw here. These three arrows tell us what we should draw. First thing, we can obviously draw all of the carbon. None of that changes. The pi bond is broken. That goes to bromine. The bromine-bromine bond has broken. These are what the first two arrows get us. Pi bond broken, new bond to bromine. Pi bond broken, new bond to bromine. Bromine-bromine bond broken, pair of electrons to bromine. Pair of electrons from bromine goes back to where there would be plus charge otherwise, and there would be two pairs of electrons that we didn't use on bromine. If we calculate the formal charge for bromine here, it would be plus. And the other detail that we haven't filled in here is that there's no way for bromine to be both up and down. It'll either have to have both bonds wedged or both bonds dashed. Either is okay. But these two bonds have to be on the same side. This is called a bromonium ion. Just like oxonium ion. Oxygen with plus charge, oxonium ion. Bromine with plus charge, bromonium ion. Carbon with plus charge, carbocation. It's not quite called the same, but it's a close combination. This species is a reactive intermediate. We don't actually make a carbocation here, so this doesn't happen. Maybe when we started this out and we just drew these first two arrows, one arrow, two arrows, this is what we might expect there. If this was hydrogen, we'd form in the previous four examples, carbon-hydrogen bond, then a leaving group, or bromine, chloride, sulfate, whatever. But this doesn't actually happen. This carbocation actually never exists because there's electrons right next door that want to close right into it. So hydrogen was what we used our first four examples with. That had no electrons, it couldn't do anything here, we had a real carbocation. But as soon as we get bromine, there's never a carbocation that's even possible of forming. So the mechanism changes just slightly, but it starts off the same. One arrow, two arrows. If bromine has electrons, it donates right back and it forms what's called a bromonium ion. Okay? So this is new. You'll get good at it if you practice it. If you don't practice it, you'll never get good at it, but that's the way anything in life goes. We're going to go back to this particular intermediate here. This intermediate is highly polarized, here to here, here to here. There's significant plus charge on this carbon, significant plus charge on that carbon. How do I know that? Well, we have a carbon-bromine bond. That's already polar bond because bromine's more electronegative than carbon. We've added a plus charge to bromine. What's that going to do to the polarization of this bond? It's going to suck it even more this way. These two carbons are highly electropositive. They really want electrons. Look what has electrons, and look what the final product is. From here to here, we have to get bromine on two different carbons. I'm giving you all the clues here. Negative charge, lots of electrons. Plus charge, plus charge. We can pick either one of these. Let's pick the lower one. This bromine is bromide. It's going to attack this carbon right here. It's going to cause this particular carbon-bromine bond to pop open. This three-membered ring is very unstable. This bromine has a plus charge on it. That's also very bad. So bromide will attack carbon from the opposite side. This bond will break. The electrons will go to bromine. You should build this with a model kit. This particular structure here, you should build your model kit. You're required to have a model kit for this course. This is one of the problems you should use it on. You should build this and see that bromide comes in from the opposite side. When we push all these arrows, this is the final product that we'll get. This top bromine came from our bromonium ion. This bromide can't come in from the top. It's too crowded here. It can't come in from the top. It's too crowded here. It comes in from underneath the molecule. And again, I think you should build this. You can build this with like a red atom here with two bonds, and you can build a three-membered ring with your model kit easily. You can also look at this in your textbook or the slides I provided for a better three-dimensional picture. We don't draw these, or this is a difficult one to draw, and even during regular lecture class, if I was at a whiteboard, I'd give you the same exact advice I'm giving you. Build it with a model kit. Look at a picture in the PowerPoint slides, the PDF that I provided.